Take a quick look around the room you're sitting in right now. The screen you're watching, the air you're breathing, the coffee cup sitting on your desk, literally everything in the physical world is made of atoms. But when you really stop and think about it, the universe is essentially a massive, messy puzzle. Without some sort of system to organize all these building blocks, chemistry would just be a chaotic jumble of reactions and invisible particles. So how exactly did we manage to organize all of it without descending into total chaos?
Welcome to this explainer. Okay, we're going to dive right into this. Today, we're putting on our detective hats and decoding the universe's ultimate organizational chart. We're going to explore exactly how early scientists wrangled the absolute chaos of the physical world into an elegant, universally understood system.
Here's our roadmap for today. We'll be hitting 5 main stops. 1. The quest for order. 2. Cracking the elemental code. 3. Navigating the periodic table. 4. The elemental name game. And finally, 5. The science of measurement. Let's kick things off with Section 1, the quest for order, from chaos to chemistry.
Imagine being a scientist in the early 1800s. You're discovering all these new elements, but you have absolutely no idea how they relate to one another. It's like having puzzle pieces but no picture on the box. Just look at how fast things moved once we actually started looking for patterns, though. In 1808, John Dalton kicked things off by assigning atomic weights to the 20 elements known at the time, theorizing that atoms of the same element are exactly the same. Less than a decade later, in 1817, Johann Dobereiner noticed something really cool. He found groups of 3 elements with similar properties, which he called triads. He actually figured this out when he realized strontium had an atomic weight perfectly halfway between calcium and barium. Fast forward to 1864, and John Newlands saw that elemental properties repeated every 8th element, kind of like octaves in music. But to make his pattern work, he awkwardly had to cram 2 elements into the same box. Finally, in 1869, Dmitri Mendeleev stepped up to the plate. He took all 63 known elements and arranged them brilliantly by relative atomic mass and their properties.
When you compare Dalton's early attempt from 1808 with those highly unique, almost mystical-looking circular symbols for his 20 elements, to Mendeleev's text-based table from 1869, the difference is staggering. Mendeleev's looks much closer to what we use today. But here is the truly genius part. Mendeleev purposefully left blank gaps in his table for elements that hadn't even been discovered yet, and he went so far as to predict their properties. When the element germanium was discovered years later, it hit the nail on the head, matching his predictions perfectly.
Moving right along to Section 2, cracking the elemental code, the universal language of symbols.
With new elements being discovered left and right, scientists desperately needed a universal shorthand. They needed a strict rulebook so a chemist in London and a chemist in Tokyo would know exactly what the other was talking about. So they hammered out a system. First up is single-letter priority. Basically, the element discovered first, or the one most commonly associated with a letter, gets to claim it. For example, C belongs to carbon. But what happens when another element starts with C? Well, that's where 2-letter differentiation comes in. Scientists use the first letter, which is always capitalized, combined with a prominent second letter, which is always lowercase. So calcium becomes Ca, chlorine is Cl, and cobalt is Co. The golden rule you have to remember here? That second letter is never capitalized. If you write a capital C and a capital O, you haven't written cobalt, you've written carbon monoxide. And mixing those up is a very different and much deadlier situation.
But of course, because science loves to keep us on our toes, there are exceptions. History kind of complicates things. Some elements use symbols derived from their historical Latin names rather than their modern English ones. This is the infamous Latin name exception that trips up practically everyone when they first learn chemistry. Copper is Cu because of the Latin cuprum. Sodium is Na from natrium. Potassium is just K from kalium. And my personal favorite, iron is Fe from ferrum. So, if you've ever stared at the periodic table wondering why on earth iron is a giant F and E, well, you can go ahead and blame the Romans for that one.
Let's dive into Section 3, navigating the periodic table, reading the map.
Now that we speak the language, let's learn how to actually read this incredible scientific map. At its core, the periodic table is simply a way of organizing all the elements by increasing atomic number. Now, what's the atomic number? It's just the number of protons sitting in an atom of that element. Hydrogen has 1 proton, so it's number 1. Simple as that. But the absolute beauty of the table's shape is that it naturally keeps elements with similar properties grouped close together.
A great way to start navigating is by looking at the basic geography. Think of it like a map with 2 massive territories. Metals dominate the left side and the middle of the periodic table. On the flip side, nonmetals are clustered all the way over on the far right edge. Let's zoom in on this map's grid system. The vertical columns on the periodic table are called groups, and the horizontal rows are called periods. This grid creates some very specific neighborhoods. For instance, group 1 elements on the far left are called the alkali metals. Over in group 7, you've got the halogens. And group 0 elements on the far right edge are the noble gases. And sitting right there in the middle, filling up that massive gap between groups 2 and 3, is a block known as the transition metals.
Section 4, the elemental name game, an interactive knowledge check.
All right, you learn the rules and you know the map. Now check this out. It's actually pretty cool. You can use the periodic table to spell out words. You can literally construct the name Bethany using just elemental symbols. You've got beryllium, Be, thorium, Th, astatine, At with a bit of a creative twist there, nitrogen, N, and yttrium, Y. When you look closely at these individual blocks, you see the atomic number, the symbol, the full name, and its atomic mass. It's an incredibly fun, practical way to memorize the elements and see how they piece together.
Okay, so I have a quick challenge for you. Let's do a mental pop quiz. Think back to our grid rules. What is the chemical symbol for the alkali metal located in period 4? Remember, alkali metals are in group 1, so we are looking for the exact intersection of group 1 and period 4. Got a guess in mind?
And the answer is K, for potassium. Remember that tricky Latin exception we talked about earlier? Kalium. If you got that right, excellent job. That means you're successfully navigating the grid and remembering those quirky historical rules all at once. Let's try just one more to really lock it in. Quick question 2. What is the chemical symbol for the halogen in period 5? Think about where the halogens live. They're over in group 7, so you just want to drop down to that 5th row. The answer is I for iodine. Group 7, period 5. Perfect. Being able to quickly pinpoint elements like this really shows you just how logically this entire table is constructed. It really is a flawlessly designed map of the universe. Finally, Section 5, the science of measurement, the bedrock of discovery. Because here is the million-dollar question. How did scientists like Dalton or Mendeleev actually figure out those atomic weights and properties in the first place, giving them the data to build this table? Well, it all comes down to physical quantities. A physical quantity is simply a property of something that can be measured. But a measurement isn't just a naked number. It is always expressed using a specific number combined with a standard unit. If I tell you a piece of copper is 5, that means absolutely nothing to you. 5 what? 5 grams? 5 centimeters? 5 degrees Celsius? Without a unit, the number is practically useless. Whether you're measuring the microscopic mass of a single atom or finding the exact angle of a chemical bond, you rely heavily on precise tools. Standard units and highly accurate measuring instruments are the absolute bedrock of all scientific discovery. Without them, chemistry is just total guesswork. Because the ultimate learning target for any scientist is perfect accuracy. Much like hitting the dead center bullseye on a target, science requires us to make accurate measurements using those standard units every single time. Honestly, Mendeleev couldn't have predicted the existence of unknown elements if the atomic masses he was working with were just rough estimates. It was that relentless accuracy that allowed him to see the hidden gaps. So, I want to leave you with a provocative thought today. Look around that room you're sitting in one more time. It's totally full of elements, metals, nonmetals, halogens, noble gases, all of them interacting right this second. If you were suddenly tasked with measuring and categorizing every single physical quantity in that room, which scientific tools would you reach for first? And what invisible patterns might you discover hiding in plain sight? Thanks so much for joining me on this explainer, and keep questioning the incredible world around you.